Alright, so we've previously talked about surfaces that might look something like this. Again, where our function f might return, takes in two variables and returns a single variable output. And, those surfaces might look something like this. And I'm going to bring in a graph over here. And, so these are 3D surfaces and modeled geometrically, essentially. And we've said, essentially, that we can kind of isolate variables x and y over here. And so by that we mean we can kind of analyze these surfaces simply in terms of x and y and analyze the change in f with respect to these variables. And so what that might look like in practice is that we, for example, might want to isolate this for a given curve. So for example, we might have a point over here, and we might simply isolate or set the y value, for example, to be a constant y value, and thus we might get a certain curve with just a constant y value. We might also get a certain curve with just a constant x value. That might look something like this. And that is the curve with a constant x value. And these curves allow us to analyze rates of change within our function f in the context of specific variables. And so we said that that looked essentially like curve 1 having values for given x values, the y coordinates of p, and then a given z value, and then almost the same thing for curve 2, except we have the x coordinate of point p and then given y and z values. We also talked about the tangents of functions, the tangents of these curves, and they could be modeled as such. So we could kind of bring down a tangent line over here, and we could bring a tangent line across over here. Looks something like this. And that is tangent number 2. And these tangents, the slopes at least, of tangent 1, for example, well, that could simply be said to be the derivative of curve number 1 at a given x value. And we call that essentially the partial derivative of f with respect to x given a constant y. And similarly, we can say the same for the slope of tangent number 2. And the slope at tangent number 2, again, is just going to be the derivative of curve number 2 at a given y value, and that essentially is the partial derivative of f with respect to y. So we basically took this idea of tangents of curves at specific constant values, and we kind of translated that over to partial derivatives. But we can obviously extend this idea further, because clearly, while we can represent tangents of specific tracings of these surfaces, we could also try to find planes or other surfaces that could represent the tangent at a specific point more generally. And what I mean by that is that we have, for example, these two tangents over here. These two lines could, for example, be contained within a larger plane. And we'll get to the idea of a plane, hopefully, possibly in future videos. But what we know for now, or what we need to know for now, at least, is that these two lines can form a plane. And that plane can be arbitrary like this for now. But what we can investigate essentially is how this tangent plane is formed and what that might allow us to do in terms of approximating certain values of functions on this surface. And so that idea is essentially known as tangent planes, and that's what we'll be talking about today. So I guess we can start off by discussing how we come about the idea of a tangent plane. Now, for starters, we can say that a tangent plane is essentially going to be the equation of a plane. It's going to be modeled by the equation of a plane. But thus begging the question, what exactly is the equation of a plane in the first place? And so we say the equation of a plane is ax minus x naught plus by minus y naught plus cz minus c naught equals to 0. Now, the reasoning behind why this is the equation for a plane is something of future discussion. For now, we can focus on the fact that this is the equation of a plane passing through a point that is given by x naught, y naught, and z naught. Let me actually redraw this 0. It looks much better. Yes, that way. All right, so this is the equation of a plane. We can manipulate this equation for the need that of trying to find a tangent plane. And so in order to do that, we might, for example, divide everything by c and transfer over a couple of things onto the other side. So watch closely. So what we've done here is we first divided everything by c, and we're going to take this term over here, this ax minus x naught, and this by minus y naught, and we're going to bring it on over to the other side. And so what that's going to look like in practice is the following. And this is just simple algebraic manipulation, nothing really big going on over here. So we've divided both sides by c, and we have brought on over two terms onto the other side. Then we can hence define two variables, just to make this a little bit more easier for us to understand. We can define two variables, lowercase a to be negative a over c, and we can also define lowercase b to be negative b over c. Therefore, we say that z minus z naught is therefore equal to a x minus x naught plus b y minus y naught. All right, so we started off with the equation of a plane. We now have a manipulated equation that we can use. But let's take this a little bit further. We know from above that the slope of t1 is essentially the partial derivative of f with respect to x. We also know that t1, the y-coordinate of t1, is composed of primarily just the y-coordinates of point P. So let me just write that down real quick. So we have this whole idea. Let me move this graph over here actually. So we have kind of this idea that the y-coordinate of t1, let me do this in a different color. The y-coordinate of t1 is going to essentially be equal to p sub y. And the y-coordinate, or sorry, the x-coordinate of t2 essentially going to be entirely composed of the x-coordinate of point x. So given these two ideas, we can find both t1 and t2 using our equation of a tangent plane that we've described at the bottom over there. And so t1 is going to be, and we use black over here, is going to be essentially z minus z naught is equal to ax minus x naught plus b y naught, or oops, I'm sorry, b y naught minus y naught. And the reason we substitute y naught into the value for y in the equation of a tangent plane to find t1 is because we already know that the y-coordinate of t1 is going to be y naught for all of its values. Hence, we can say that y naught minus y naught is essentially 0, and therefore the simplified equation can be said to be ax minus x naught. All right, we can do the same thing for tangent number 2. Tangent number 2 is going to be z minus z naught is equal to ax naught minus x naught plus by minus y naught. Again, we can say that x naught minus x naught is equal to 0. Therefore, it is equivalent to simply by minus y naught. All right. So we have two simplified equations that represent both tangent number 1 and tangent number 2 of the above surface. And so we notice that this kind of looks much like point slope form. And this is point slope form is something from Algebra 1 that we might remember. And so the key here that we want to really kind of hone in on is what are these values of a and b? Well, we know from algebra that algebra 1 that a and b are essentially the slopes of the respective lines t1 and t2. Well, we know what the slope of t1 and t2 are. They are essentially the partial derivatives with respect to both x and y respectively. Let me write that down real quick. So basically a is essentially going to be del f del x, and it's going to be the partial derivative of f with respect to x at a given point, that point being x naught y naught. Similarly, b, the value of b, is going to be the partial derivative of f with respect to y at a given point, again, x naught y naught. So given all of this information, we can say that the tangent plane equation for at a given point can be defined by z minus z naught is equal to the partial derivative of f with respect to x of a given surface at a given point multiplied by x minus x naught plus the partial derivative of f with respect to y at a given point multiplied by y minus y naught. All right, and so given this, we can say that this is definitively the equation of a tangent plane. That is the general equation of a tangent plane, All right, so why don't we take a look at an example problem of what a question might ask when asking us for the equation of a tangent plane. All right, this question is asking us to find an equation of the tangent plane for the following surface at the specified point. The surface here is z equals 4x cubed plus y squared at the point 1, 1, 5. All right, so first we need to find the partial derivative with respect to x and y for this surface. So let's start by calculating that. So del z over del x. So first we're trying to find the change in z with respect to x. That can be defined as 12x squared. Next we calculate the partial derivative of z with respect to x at the point 1, 1, 5. And so that is simply going to be equal to 12 times 1 to the power of 2. So 12 times 1 to the power of 2 is simply 12. And so there is our quote-unquote a value. Now we can do the same for the partial derivative with respect to y. The partial derivative with respect to y. And that is going to be equal to 2y simply. So it's just going to be 2y. And translating that over to a specific point, the partial derivative with respect to y at the point 1, 1, 5 is going to be equal to 2, because 2 times 1 is simply 2. All right, so we have our two slopes over here. We also have the z value, and so hence we can find the equation of our tangent plane. So using the general equation of a tangent plane, we can say that z minus 5 is going to be equal to 12 x minus 1. We're using the the x-coordinates of our given point plus 2y minus 1, the y-coordinates of our given point. We then simplify this equation to become 12x minus 12 plus 2y minus 2 plus 5, which is equal to 12x plus 2y minus 9. And so thus that is the equation of our tangent plane. Whoops, let me box that correctly. Now, you'll notice that this original surface is actually a little bit familiar to the surface that we used earlier for our earlier example. In fact, let me show you how this surface compares when plotted against this tangent plane. Alright, as you can see, let me zoom in just a little bit. As you can see, we essentially have our original plane, which is in red, z equals 4x cubed plus y squared. And then we have the tangent plane, which is in green, which is going to be 12x plus 2y minus 9. And then we have that small point over there, 115, and that is essentially the intersection of both of those surfaces. Let's look at another problem. Alright, similar to the previous problem, this problem is asking us to find an equation of the tangent plane for the following surface at the specified point, the surface being z equals x sine x plus y at the point negative 1, 1, 0. Alright, so we first calculate the partial derivative of z with respect to x. Well, that's simply going to be, well, we first need to use product rule here, because we have two x-containing terms. We have x and then we have sine x plus y. So first we calculate the derivative of x, which is simply 1. So we have sine x plus y plus, now the derivative, now we're keeping this x, and now the derivative of sine x plus y, treating x as a constant, or sorry, y as a constant, well, that's simply going to be that's simply going to be cosine x plus y. In fact, we don't even have to do chain rule on it, because the derivative of x plus y is simply going to be 1, as long as y is a constant. So it's going to be 1, and we're left with the original expression. So the partial derivative with respect to x is going to be sine x plus y plus x cosine x plus y. Calculating the partial derivative at the specific point, in which case our point is negative 1, 1, 0. Well, that's going to be sine x plus y, so x plus y, or aka negative 1 plus 1, is 0. So sine 0 plus negative 1 times cosine 0. Well, that's simply 0 minus 1. And so the answer, in terms of the partial derivative, is simply going to be negative 1 for the partial derivative of z with respect to x. Similarly, we can do the partial derivative of z with respect to y, and that's, we are not going to have to need product rule for that, because we're treating x as a constant. Therefore, we simply have to derive sine x plus y, treating x as a constant. That leaves us with x cosine x plus y. Calculating the partial derivative at the point, at a given point, and that point being negative 1, 1, 0, that leaves us with negative 1 cosine 0. Hence, we simply can just say that the partial derivative of z with respect to y at the given point is negative 1. Alright, so we have calculated both partial derivatives. Now we have to kind of summate it into a general equation for a tangent plane. We do that first. We use the z value at the given point, so the z value is 0. Z minus 0 is going to be equal to negative 1 x plus 1, because the value, the x-coordinate is negative 1, and so x minus negative 1 is x plus 1, plus negative 1 times y minus 1, The value for the y-coordinate we're using is 1. And now we can simplify this to simply be negative x minus 1 minus y plus 1. These two 1's cancel out each other, and thus we are left with the equation for the plane being negative x z equals negative x minus y. Alright, let's take a look now at the idea of linearization and linear approximations. Alright, this question is asking us to find the linearization L of xy of the following function at the given point. The function being f of xy is equal to 1 plus x ln xy minus 5, and the point being 2, 3. Okay, so let's break this down step by step. What is linearization? Well, in calculus, a linear function whose graph is the tangent plane is called the linearization of f at a given point, and we can subsequently also calculate the approximation. I'm going to show you what this means in practice using the given problem. So first, we can calculate the tangent plane of the following function using the partial derivatives. So what are the partial derivatives? Well, the partial derivative of f with respect to x is going to be, well, in order to calculate that, we first need to we have to use product rule, clearly, using this term, because this one just amounts to 0, essentially. And so we're going to have to use product rule. So the derivative of x is simply 1. So we have ln xy minus 5. And then in order to use product rule, we keep that x for the second term. And for the second term, what we have to do is we have to derive ln xy minus 5. Well, the derivative of ln xy minus 5 treating y as a constant is simply going to be 1 over xy minus 5. Whoa, that was a terrible y. And we also have to use chain rule here. So the derivative of negative 5 is going to be 0, and the derivative of xy treating y as a constant is going to be y. Okay, now we can do the same thing, but for the partial derivative of f with respect to y. Similarly, we don't have to use product rule. However, we do need to derive this ln xy minus 5 over here. We can use the same process, except in order to do chain rule, we have to take out the x instead of the y. So let me show you what that means in practice. So in practice, we have the x over here, 1 over xy minus 5, because that is the derivative of ln xy minus 5. And then we're multiplying that by the derivative of xy minus 5, treating x as a constant. And so therefore, x is just going to be taken out, and that's going to be our derivative. All right, let me simplify this just a bit more for the sake of simplicity. Okay, so we have these two partial derivatives in front of us. Now we have to calculate their values at that specific point 2, 3. So let me go down here just for a second to give us more space. So our point here is 2, 3. And so using the partial derivative of f with respect to x, we know that the partial derivative at the given point, 2, 3, is essentially going to be ln 6 minus 5, because 2 times 3 is 6. So ln 6 minus 5 plus 2 times, again, 6 minus 5 times 3. All right, let's do some quick maths. Ln 6 minus 5 is the same thing as ln 1. Ln of 1, if you don't know, is essentially 0, because e to the power of 0 is 1. So we have 0 plus 2 times 1 over 6 minus 5. 1 over 6 minus 5 is 1. Therefore, 2 times 1 is simply 2. Times 3 is going to be 6. So 0 plus 6. Hence, we're just left with 6. Let's do the same thing, but for the partial derivative of f with respect to y at the point 2, 3. Well, we have essentially 2 times 1 over 6 minus 5 times 2 again. Once again, 1 over 6 minus 5 is boils down to just 1. So 2 times 1 times 2 is 4. Alright, so we have our two slopes over here that we're going to be using for our two tangent lines. So now let's calculate our z-value, because we have yet to have a z-value. We have our the x naught, our y naught, we have our two slopes, but we don't have a z-value. So let's first remind ourselves of what the actual function is. And the actual function is going to be 1 plus x ln x y minus 5. And so plugging in the values for x and y, that leaves us with z is equal to 1 plus 2 times ln 2 times 3 minus 5. That simplifies out to, once again, just 1. That the reason behind that is because ln 6 minus 5 is, again, 0, so 1 plus 2 times 0 is going to be 1. Now that we have our z-value, we can actually calculate the linearization. The linearization is essentially going to be the linearization at 0.23, to be more specific, is simply going to be, when subtracted by 1, is going to be the slopes, which are 6, x minus x naught, which in this case is 2, plus 4 y minus y naught, which in this case is 3. And so we can simplify this out to become the linearization at the 0.23 going to be equal to 6x minus 12 plus 4y minus 12 plus 1, which is equivalent to the linearization at the 0.23 being equal to 6x plus 4y minus 23. So that is the idea behind a linearization. We are essentially trying to find the linear function whose graph is the tangent plane. And so it is very similar to, in fact, the tangent plane. In fact, you can find the tangent plane first and just set that equal to the linearization. But I kind of showed you how to do that in more technical terms instead. Let's do one more problem involving linear approximation. Alright, this problem is asking us to linearize the following function at the given point, and then to use the linearization to estimate the value of f of 0.9, 3.1. And the function we are given is f of x, y is equal to 1 plus y over 1 plus x at the point 1, 3. Alright, so in order to do this, first we need to calculate the linearization at the point 1, 3. And before all of that, though, we first need to find our partial derivatives. That is kind of the basics of all these problems. So to start off, we are calculating the partial derivative. Let's kind of simplify this function for us, because that fraction is annoying me. So f of xy can be said to be equivalent to y plus 1 times x plus 1 to the power of negative 1. Okay, so since we have that out of the way, now we can kind of derive in peace. So we have del f over del x. So we're calculating the partial derivative with respect to x. We're treating this term over here as a constant. Therefore, we can bring down the negative 1 using power rule and then change that over to a negative 2. So we have negative 1 plus y, x plus 1 to the power of negative 2. In fact, we don't even need to use chain rule over here. Or, I mean, we need to use chain rule. However, it really just amounts to the same expression. We can now calculate the partial derivative at the points 1, 3. And so that is simply going to be negative 3 plus 1 times 1 plus 1 to the power of negative 2. That is equivalent to saying negative 4 over 2 squared, which is negative 1, because 2 squared is 4. Alright, let's do the same thing, but now for the partial derivative of f with respect to y. Let me rewrite that f. Okay, so yet again, we are treating this term over here as a constant, and so thus, in fact, I think we don't really need to do anything much besides reducing this to just 1, or this y plus 1 to just 1. And so what we're left with is essentially going to be 1 over x plus 1. Or sorry, yeah, x plus 1. Okay. All right. Now we need to calculate what the partial derivative of y is going to be at that specific point 1, 3. So first we all we need to do is use the value of 1 and plug that in to x, and so what we're left with is simply 1 over 2. Alright, so we have our two slopes. We can now use that to find the linearization. So to find the linearization, we first need to find the value of z. So actually, let me just write this down. So f of 1, 3. Well, that's simply going to be 3 plus 1 over 1 plus 1, which is the same thing as 2. Because we have basically 4 over 2, so that's equivalent to 2. Alright, so now we can calculate the linearization at the point 1, 3. So the linearization is going to be, well, L of 1 over 3 minus 2 is going to be equal to negative 1 x minus 1, because we're using the x coordinates of the given point, so which is 1, plus 1/2 y minus the y coordinate, which is 3. And now we can simplify this over. So we have L of 1 over the linearization at the point 1, 3 is going to be equal to negative x plus 1 plus 1/2 y minus 3 over 2 is plus 2. So that is essentially the linearization. We can simplify this a little bit more to be equivalent to negative x plus 1/2 y, and then we can add 1 and 2, 1 and 2 over here, so that gives us 3, and 3 minus 1.5 is just 1.5, so that leaves us with 3/2. And so that is the linearization. But we're not done yet. The question asks us to not only linearize the function, but use the linearization to estimate the value of f of 0.9, 3.1. So that is the real question. So we are trying to find what the value of f of 0.9 and 3.1 is. Alright, so in order to do that, it's, because we're simply estimating, we can just plug in the values of the x and y into this linearization. So hence, we can say that the value of f of 0.9, 3.1 is going to be negative 0.9 plus 1/2 3.1 plus 3/2. Alright, if we want to simplify this even further, we can say that negative 0.9 plus 1/2 times 3.1 is the same thing as saying 1.55. And so let me write that down, plus 1.55 plus 1.5. I like dealing with decimals more than I do fractions. Alright, we can simplify this even further to become 0.6 plus 1.55. That is simply by adding, or sorry, we can simply by subtracting 0.9 from 1.5. And then we're left with 0.6 plus 1.55. Adding those two together, we are left with 2.15. And so that is our linear approximation. In fact, if you do calculate this, and I encourage you to actually go ahead and calculate what the value of f of 0.9 and 3.1 are is, and I think that should get you about 2.157. And so if we compare that to our original approximation, it's pretty darn close. I'll be leaving a PDF of this whiteboard in the description of this video. Thank you so much for watching. If you have any questions, please leave them in the comments and I'll try to get to them. Otherwise, thank you for taking the time to watch.